you very much. Yes, hello everybody, good morning. It's a lovely morning, quite early I'm sure. So I'm Andrew Godwin. For those of you who don't know me, I am a Django core developer. I'm also a senior software engineer at Embiez these days. And I'm also the person who sort of created and still maintains SAP for migrations. So my part and perspective in Django is very much that of migrations and schema design. I usually give a talk at DjangoCon about migrations. This talk is a bit different. I'm moving more towards a general how databases work and how you should sort of design tools for them. Christoph Pettius' talk from yesterday, it's also worth seeing in that regard, but it's a sort of different angle on that kind of stuff. So first of all, I want to talk about schemas. There are two kinds of schemas. Most of what you would think a schema is an explicit schema. It's one that you define with columns, with types. You sort of go and declare tables and relations and that kind of stuff. But there's also implicit schemas. These are schemas that your data has, but you sort of, they're not declared anyway, they happen to be that way. You know, if you're writing records into MongoDB, they're still got a schema. You're still expecting to see a name field that looks like a string, or an age that's an integer, but they're not declared anywhere. And in fact, they change over time. So you can sort of group databases into two different kind of schemas in that sense. So things like Postgres, MySQL, Oracle, SQLite, they're standard relational databases. They have declared schemas. So you say, here's a table, it has these columns, there's these constraints, stuff fits in this way. Things like CouchDB and MongoDB are document databases. You just fire JSON at them and you just split it. Again, there is no explicit schema, and you can store things that don't match. But your records do have one or more implicit schemas. And as we'll see in a second, that can be a big problem. Redis and things like ZODB are similar. ZODB is the SOAP object database, it's back SOAP, which I'm sure some of you will be familiar with from clone and things like that. It also stores arbitrary sort of objects in the tree, and Redis is a key value store that has a few set types. Redis is the least schema-y, it's more key value, but there is still some, your code assumes some layout of all the databases. Like, if you're using Redis, you assume a certain kind of key, you assume a certain kind of value. So there is still assumptions here about the schema or the type of data you're putting into the database. So as an example, we have two different things here. So the top one is a standard relational schema. You can see it's got an ID column, a name column, a weight column, things like that. And then the bottom one is how it would look more in something like Mongo. You've got sort of a standard free-form dictionary, it's got an ID and a name sort of field there, but those are optional. I could just have a different kind of field. In fact, that's half the problem. Go to this slide here. Some of the problem with the implicit schema is there's silent failure. Now, as you can see here, this top left example here is perfect. There's an ID, there's a name, there's a weight. That's all fantastic. But over here, I have the weight here is 85 kg. It's a string. It's a string 85 kg. That could be valid. Like if it's storing units, that's great. But that does not match this, and nothing's called that error. Over here, I have null rather than name. So obviously my localization thing has failed here. It's localizing the strings for the keys and this stuff, which is not great. And then over here, I have a negative weight. So all these three examples here are wrong. But unless your code is being very stringent, you won't catch them. So you are relying on this schema here, even though it's free form. So your code assumes something, there is an implicit schema there. And sort of typical examples of how this manifests itself is that generally an explicit schema is a relational or normalized data structure. You have very declared tables, you join between them, and sort of you know exactly what you're dealing with. And implicit schemas or document databases are usually embedded structures. So usually you'll find that rather than having different tables and joining between them, you will instead have, say, a user document, and inside that a list of favorites with that embedded inside it, and inside the list of favorites, details about the list of favorites themselves and their titles. And so that works great, and it means you can join directly. Joins are essentially eliminated, but you are sacrificing the writability. When you are writing new records, if I say if I change the name of a page, I need to change the page, and every single favorites entry that has the title of that page. So suddenly, changing things is much harder on the database. So there are trade-offs for both of these. But the other thing is, schemas aren't just for validation. Like, they're really good for checking the data is correct, but they also, databases realized quickly early on they're a great way to work out how to store stuff. If my column is an integer, I can store it a lot more efficiently than I can store a string. if I've got 8 booleans, I can pack them all into 1 byte, for example, if I really want to. And so there's a lot of stuff here about how schemas inform storage. Postgres in particular is the least surprising of all of these. Postgres is very flexible, it has lots of different types, it moves very well, and so like in terms of comments about differences in databases, Postgres is just sensible. Some interesting points about Postgres. We have the fact that adding nullable columns is instantaneous, which is a fantastic thing for deployment. So not people know this, but the nullable here is very important. But as long as you have a nullable column, Postgres will return pretty much instantaneously and with like literally no logging at all. It has to be at the end of the table, one restriction, but Django doesn't really do positional comments, so that's fine for us. So yeah, this is great. In MySQL, this same operation can take hours or days sometimes. Another good thing that Postgres has that isn't often known about is create index concurrently. Now usually when you create an index, Postgres will freeze the table to read all the rows and then sort of take them into its index. This instead does that in the background to sort of catches up slowly to new data. It can only do one at a time and it's slower, so it's sort of a trade-off there. But if you've got a giant table you want to add a new index onto, this is great, because this means you can just fire it away, queries keep running properly, it slows down a little bit, but it's much more manageable than just having everything stop. There's also some wonderful things where, Postgres has a fantastic constraint syntax. In particular, you can constrain by almost anything, especially like expressions, or if this is less than this, greater than this, or these ranges don't overlap. You saw Mark's talk on Tuesday. But you can also add constraints after you add the columns. And the key thing here is that when you add a constraint, Postgres has to scan the entire table and make sure all the rows match the constraint. Because obviously, you are telling the database, I now trust you to say that all of these rows match this constraint. So when you give it one, it goes, okay, well, I need to go and check all the existing data. And so what you can do is you can make the columns first, and then have data there available, and then make the constraint afterwards. And so that like this two-phase addition means that you are not blocking on that additional column addition, which is quite nice. MySQL is a lot worse, obviously. I have a entirely justifiable issue with MySQL. But some examples here that MySQL often locks the whole table. So if you add a column, MySQL will just lock the table and rewrite the entire file on disk, which will take ages. It also doesn't support transactions around adding and removing columns. So if for example, I'm adding 2 columns and I add the first one, great, fantastic. Add the second one, it fails. I'm suddenly left with only 1 column added, and I can't roll back because there's no transactions. And so it's very easy to get yourself in a very difficult state of MySQL, because you end up in this horrible state where, well, half my migration applied, half it didn't. I need to go manually log in and unpick them. That's not great. Other databases have different problems. Oracle has a very short character limit. Microsoft SQL Server has other problems with things like defaults and types. If you're using these, it's worth learning something about how they work and their strengths on certain different types of database. Things like the string type and block type vary a lot. Different storage and different performance characteristics. So it's worth giving some thought to the particularities of your database engine. But the key thing that I'm involved in here is changing schema. Now, schema is great to do a 4-month-long specification process. We go, okay, we've examined every part of the business, we've worked out on this giant piece of paper a fantastic wonderful schema, and it's perfect. And then the next day, someone goes, wait, we've got to tell you about this. But schemas change. No schema is ever fixed. In particular, you can't version control schemas like you do code. And the key thing here is that you can't put your data in a VCS. Because if you did that, you'd have a copy of your data for every point in history and it would blow up to a massive size. You can put schema definitions into a version control system, that's fine, but your data won't match. As you jump around branches, you're going to lose. If I add a column on one branch and I add data into it, that's great. If I switch back to one where the column isn't there, I'm probably going to lose that data. Like I'm telling my database, this column not there anymore. And so it's going to go, okay, great, storage, free it, and then just delete the data. And so Django migrations are designed to be this kind of thing, where you have a way of specifying schema that you can store on disk. In particular, the new migrations are much shorter than the old ones, as you can see here. So anyone who's used South, you'll realise that migrations usually would be this long and then go down into the earth around 500 meters after this. This is much shorter. So these are the new 1.7 migrations for those who haven't seen them. And so the plus side here is this is a lovely, small, codified way of saying, well, this migration, that makes a model. And with that, you can just sort of build these things up and sort of combine it together. Migrations aren't enough by themselves. Databases are a very fixed point in terms of coding. You have to be very careful around them, you have to be very thoughtful. And so you still need to have some social interaction, some coordination in your team when changing schema. In particular, dropping columns or changing tables from two people at once isn't going to work well. So the key thing here is make sure that if you are both changing schema in a team, there is some coordination there. Django migrations will tell you when you have some kind of conflict in your merging of two branches. It doesn't do much past that for you. Just go, there's an error, and then just throw its hand up and stop. And then you can spend like half an hour manually fixing it. So please be aware that you can't just, as you do with code, just all work on feature branches and expect it to work. But you know, with all this in mind, schema seems quite limiting. Like, what have we got rid of the schema? Like, it's just sitting there, it's just being annoying, it's just stopping us changing stuff. What if we go for a brand new world, for a document, and MongoDB, and yeah, it's great, right? Here we go, look, here's a document, it's fantastic. I've got all my stuff embedded there, I can add new fields, there's no joins, so I can store my friends as sub-object, that's fine. That's fine, apart from the fact that, as I said earlier, I've got users everywhere here. Like, I've got this is a user, these are users, this is a user down here as well. Like, if I need to change Mass's name here, I need to change her user record, I need to change every single friend list she appears in, I need to change every single like list she appears in. So, suddenly changing something is a massive proposition that locks a lot of different parts of the database. So you might be thinking, well, what if we take that user record and have it only in one place, and then have some kind of ID pointer? Congratulations, you've invented joins. And suddenly you're doing joins on a database that doesn't support joins and just does Cartesian product, and then you're basically lost. And so, some data fits this pattern really well, but also joins aren't bad. Joins are a really good way of having data that is shared between different parts of different parts of the schema without having to write it all at once. Certainly, if you've got a massively read-heavy load, this could be really good for you. So this is almost a pre-optimization, as you were. Like, well, we can do all the work up front of writing it in places and save that later. But a lot of websites aren't that read-heavy. But you also don't have to use a document database. Like, it seems like, well, I have seamless data, like, for example, CMSs, or you have like random user profile stuff. And in a traditional relational style, you would have, we have page, we have page attributes, which is a table of page ID, property name, property value. This is a pattern called EAV, entity attribute value. It's very common in relational databases. It basically just has a table that is a dictionary mapping of stuff. It has an extra join, so it can be quite slow. But that's not necessary. You can instead just put that data in a column by itself. So Postgres has a JSON data type. It's not perfect, but it works pretty well. 9.4 improves it. But most of the time, you're querying on a few columns. Like, say I've got user profile pages. You look it up by username. You look it up by perhaps, you can sort it by a few other things. But most of the time, I don't want to query for everyone whose page is blue. Like, that doesn't make any sense. And so I can justifiably have all this stuff here be in one big blob column and say, well, when we fetch the row, we'll read it out and decode it. That's fine. But I never need to query it. Like, it's not that important. So suddenly you've got this thing where all the columns that actually sort of use at query time are full columns, are properly indexed, all that kind of stuff. And all the sort of the free-form columns can just be over here. There's nice big JSON, and you can do it on MySQL, you can do it on Oracle. It can just be a text field that has the stuff in it. And that works reasonably well. And because obviously when you change one thing in here, you rewrite the entire block. So if it gets too big, it gets a bit slow. But generally, this is a really good solution to that problem of EAV. And in fact, this will often speed up your retrieval if you were already fetching all the EAV rows before, because suddenly, rather than doing a join, you're just doing one row split with a big thing here. Now, there is a downside here. If this column gets really large, you're hurting the performance of this table, as I'll come to in a moment. But it is generally a good pattern that I don't see nearly often enough, so do think about it. So you'd think that storing JSON in a relational database must be slower than MongoDB, right? Right? Well, here is an entirely untrustable benchmark. One of the things being worked on for Postgres it's not in master yet, but it's pretty close. There are new kinds of index types, especially for the binary JSON format. In particular, there is one I was looking about, which is called JinHash, which is a special type of the Jin index, the generalized inverted index, designed to be very good at doing the binary JSON queries. Now, this is a comparison of, probably unfair, from the blog of the author, so probably biased, but I'm inclined to believe it, of MongoDB versus this new JinHash storage. Now, as you can see here, Postgres is much faster at loading. That's expected, it's much more mature. Mongo is traditionally very slow at writes, and has very bad locking semantics. Sequential scan of the data, again, very, very comparable here. Both Mongo and Postgres are just reading rows on disk, that's expected. But then down here, this is querying where we're going farming all rows where some key, some value. And Postgres is actually faster, which is ridiculous, right? Mongo is a database essentially designed from the ground up. Postgres is just a general one with an index ID. But because Postgres has all this history and all this mechanics in there, it can perform the same as Mongo. And so suddenly, all the arguments for having a separate database are essentially gone. Still, the query syntax is different if you prefer that kind of stuff, but the query syntax for binary Postgres JSON is pretty nice. You just do things like find fields where this arrow this equals X, and it's very readable. So it's one thing to do, don't just rule out Postgres for storing this kind of stuff. This isn't in Postgres yet. I'm not going to do that. This is probably a year or two away from being in a release you can use. But even currently, these are I think so. It's only about 10 times more. And bear in mind, in Postgres, you can index any arbitrary expression that is predictable. So if you want to, you could make an index on the look of expression you're looking for and have something approaching this even now. But this comes to the different ways of load shapes. Now, a lot of people, when they're designing databases, they plan either for right now or for, well, obviously my site will be really, really big and massively populated in around 2 years. So we'll design this huge scalable architecture that will work perfectly. We have 4 million customers, which doesn't work perfectly now. So there's kind of sort of 3 different things pulling you here. There is a read-heavy load. So, for example, a site that has lots and lots of reads but very few writes. This could be things like a blog, for example. There's a write-heavy load. Write-heavy loads are things where nearly every single touch of the database is a write. So logging is a very good example of this. It's very, very, very heavy on the writes. And so you want to optimize to make the writes faster, and reads are sort of lower priority. And finally, you've got very large size. As you grow in size, you can get away with less and less. Things that fit in caches, things that fit in memory, things that fit on one server, and so you sort of optimize away and you give up certain things. So here's some entirely arbitrary points on a triangle. So as an example, a read-heavy example, so a few of these I've worked on, a TV show page for a national TV show, that is literally only ever read by people. In fact, you can statically publish this as HTML and it would be fine. That's just, here are the actors, here's the episodes, change it once a week when you want it. It's the writes are literally once a week. And that may as well be 0 in database terms. Except at the other end down here, you've got logging is a very write-heavy load. Logging is literally just pushing things onto a disk, and then very occasionally you go, oh no, there was an error, and somebody goes and reads it. But they read it again once a week, and that's basically 0. And so these 2 different ends are optimizing entirely differently. And then again, you've got very large size. If I have 3 or 4 petabytes of data, it's not going to fit on the server, at least not for now. And so you have other things like Amazon Glacier down here that are using optical media and other things to store these incredibly large amounts of data in a very affordable and accessible way. The query time down here is several hours, but it's very cheap to store large amounts. You can have all 3 of these at once, it will cost you a lot of money. So imagine this is 3-dimensional, 4 factors here is money that comes out of the screen. The more money you have, the more is possible, but you probably don't have that much. And so some more reasonable examples. Wikipedia is mostly reads, but it's also a reasonable size. Now, Wikipedia text alone is quite small. You can fit the whole of the text of Wikipedia onto an iPhone, for example. But with all the media, with all the translations, all that kind of stuff, Wikipedia grows reasonably large. And it also has some rights too, but it's mostly, like, the large majority of that is read traffic. Like, people all around the world, trying to work out, what kind of TV show was on, or like, what is this, or what's going on, or trying to find bad facts about celebrities. On the other hand, so it's like this about Minecraft forums is much more of a balanced load. The forum is very interesting because the forum is very, very write-heavy for a website. Forums are encouraging the users to post comments. Having those comments appear quickly is very, very important to the site's meaning and structure, and you don't want to have things clash. You don't want to have sort of one post, 2 people reply, nobody sees the other's reply for like a minute. That's not great. And so you have this sort of prerogative to have stuff appear on the screen as fast as possible. At the same time, you have 3 or 4 million people trying to post at once. And so this doesn't end terribly well. And also, that gets quite sizable with like screenshots and things. And then Eventbrite is, again, a different thing to where I currently work. We have almost 2 different dots on this chart. Like, our main site is quite read-heavy, like sort of just listing event pages. But then the ticketing backend is very write-heavy. Like, when, for example, BlizzCon went on sale last week through us, we were seeing 5,000–6,000 requests a second just trying to buy tickets. People going, I need to buy tickets. And at that point, we're trying to sort of get all these people on the internet into a virtual line and hit the first X of them. And that itself is a very difficult process to do. And so you can imagine that most different products will sum run this diagram. You have different priorities depending on what you're trying to do. And it actually turns out that in a rough way, this maps to kind of the way you're storing your data. This is an entirely unscientific diagram that you should never trust, but it's pretty. And so, as you can see here, you've got read-heavy, generally you want to cache it. So Redis and Memcache are a good example of this. Like, if everything is just being read, even using Nginx instead of static files, it's going to just cache stuff in memory or in the files and cache eventually. So that's very practical for small read-heavy loads. And also, it can be, you can give the writes to if your writes are on the same box. And as you come down away from the reads, you get less and less indexes because as you add indexes, you add time to the writes and you add space to the storage. So every index I add to my table makes the writes a little bit slower because the writes update one more index every time. And in fact, one of the big problems in people who have just learned databases is adding too many indexes. You will massively slow down your writes and make things massively worse. So don't just add indexes to everything you want. Just sort of step back and go, well, this should have an index. And this probably shouldn't. Don't query about it, but this should have one. And in particular, things like Postgres have partial indexes, so you can have indexes only on certain parts of the data set. So if you know that you only ever look for people by age if they are in a certain program, or sort of like a certain field is true, you can index just on that and save storage space. And that kind of comes down to the large size. And you come down this branch here. The size of storing this stuff gets bigger and bigger. And especially when you've got several petabytes of data, having indexes increases that by a reasonable amount. You still need them. In fact, offline storage relies entirely on indexing. If I have a library of 40,000 CDs, I need some way of knowing what's on each CD. I can't sequentially scan them all. Just go, okay, right, it's not that one, right? No, not that one. So you have a big dictionary of, well, file 5 is on disk 49, and then you go and get that disk, put it in, and so on. And so that's kind of a different storage. And then getting down here, you have sort of more optimized formats for append-only stuff. So a log file is, in a very simple sense, an append-only database. Like, you write lines to the end of the file. That's kind of just how it works. You can read it by casting it, but there's no way of looking up lines in a file without grep or something, right? It's not optimized for reading. It's optimized purely for writing. It's very good at that. And so, this kind of balance is like, well, where do you sit? Like, how many indexes do you want? What kind of storage do you want? And the key thing to remember is that your position on this kind of diagram changes over time. As a brand new website, you're probably not even caring about this kind of load. Like, you're so small, it doesn't matter. But as you grow bigger, as your users do things you didn't expect, you'll find that you change. For example, at Lanyon, or a company that Eventbrite bought I used to work at, we started off with a very read-heavy load, where we're like, okay, well, our entire core business model is like descriptions of events and that kind of stuff, so that's great. We have a read-only mode that works really well. But sort of, as you go through it, you realize, well, our users are writing more data and they're sort of interacting more and they're trying to, and like, you start seeing different pain points in your infrastructure. And the key thing here to consider is that those pain points often are predictable and often will happen when you don't expect them. And so don't like have a fixed plan in place, unless you know what you're doing and you're experienced and you have an obvious growth path. But if you are just starting out or a small company, don't expect that your problem in 5 years' time is going to be, well, we're going to have this massive indexing problem, so we're going to move everything to Mongo and be much better. It's like, that might work. But just consider things like, well, we might have everybody trying to upload loads of images. We might have everyone trying to use some kind of file store. You know, things like Bitly, for example. Like you'd think there's a relatively obvious scaling path there. Well, Bitly is just a thing of like you have a web address, it goes to a web address, it's a key value store. But actually, they end up doing analytics and stuff. And so their load stuff now is about, well, we need to store every hit to the URL. That's actually quite a write-heavy load and that kind of stuff. So they've changed a lot over time as well, just what they're doing. And so there is some general advice here that is highly generalized and probably applies to you but may not do. So in general, if you're write-heavy, have fewer indexes. You want to make sure that your write blocks as quick as possible, so you're not blocking everything else. In particular, you can block your entire application thread if you've got too many write blocks, and that's bad. There are several stories of sites that were perfectly fine until their writes spiked just the right amount, and suddenly web processes start backpiling up. So yeah, like everything's waiting to write the database, nothing's coming in, all the processes die, and suddenly the site's not responsive. It's a very easy thing to get into without realizing it. So writes are very important. Most of you aren't going to be doing writes and saying, write, and I don't care, and then return. Like you'll be writing and waiting for confirmation and then returning the page. And so you are highly dependent on that write returning in time. Again, if you're read heavy, the opposite thing is to denormalize. So this is kind of moving towards that repeated data you saw in the example of Mongo before. You want to move data to where it might be used more, like at write time. So for example, say I was doing a site that had users who had forum posts. I might denormalize the username onto the forum post. And then rather than, well, I need to show a list of forum posts, I'm going to select forum posts, and then join on user, and then select users as well, and then match them together and take them through and whatever. You could just have enough data on the forum post to make that part HTML. You just have the username and a join date. And suddenly you've got one query, it's a lot less work, and sure, you're doing the work at write time, but you'll probably see a lot more reads of that long row than you are writes. And so you're optimizing up front for a much bigger return later and making things quick. Another very important thing that Christoph alluded to yesterday is please keep different kinds of data away from each other. Keep large data away from small data. Keep slow data away from fast data. In particular, don't have a really nice compact table full of things you update all the time and then one giant row you never touch, because suddenly you're incurring a penalty inferred by the other fields for all the small writes. Don't have a table that's written all the time on a machine that does a lot of slow, generalized queries, because you're going to be flushing the cache of that server with all the small queries when you actually want to be doing the big storage. And so, you generally want to keep your different loads, if you can, on separate servers even, not even on separate tables or instances. But generally, like, separate tables is good as well. You can have, in Django in particular, you can have one-to-one fields between different tables and models. You can store, for example, all the common user fields on one nice small user model, and have all the extended profile stuff that you should see on one page of the site and one other big one. And then, everywhere you're joining as a user, you join as a nice small table, that's great, it's much faster. But if you really want the big stuff, you can join through user to the other table, and then it's slower, but you get the big stuff through. And you've saved 90% of the time on the site for the other pages, at a slightly higher expense for one page, but it's really not noticeable. And similarly as well, databases come in every shape and size. There is relational, there is document, there is key value store, but there's also graph ones, which are not very useful in production. There's file systems. File systems are databases too. A file system is a really good key value store for large blocks. File system is designed so that you give the file system a key, the file name, and it returns you the file, the data. And so it's actually entirely feasible to store stuff on disk, because that's, disks are good at storing stuff, and they have been doing for like 30 years now. There is a lot of research into file systems, and they're really good at this stuff. So for logging in particular, the Unix model is very good at appending lines to files. There's a whole open mode just for that. And so, if you really want to store stuff sequentially in order from some kind of log, then the append mode might be for you in files. It doesn't scale very well across servers, but you can merge things across the network really well. There's other ones too. There's plenty of different kinds of databases. Some are more specialized. Things like Cassandra and React sort of generalized distributed key value stores. They get certain things. But they have the price of eventual consistency. So you have to design knowing that, well, not everything will match at once, right? Which is not good for things like, say, finance, where one person sees £1,000 in their account, one person sees minus £1,000 in their account. That's not great. That's under panic. But for things like websites, it works perfectly fine. So this all comes into sort of a set of lessons I want to sort of have you take away here. The first one is, as I said before, reevaluate as you grow. Like, you will start off with a pretty workable schema, with a pretty workable set of databases as you start out. As you grow, your needs will change. And a lot of companies are very resistant, like, well, we spent all this time invested in the database before, going, well, we don't want to change it right now. But it's worth looking at. Like, even if it's not doing the change itself, it's worth taking that problem, looking at it and saying, well, it will cost this much, or you're looking at what you're losing, like, we have this much performance penalty by living on it. And then sometimes you actually want to change. For example, change database, change style database, change your schema design, change the storage, and in some cases, you might want to make product decisions based on this. Now, it's traditionally said that it's a very bad form to have design informed by engineering, but sometimes it's very valuable. There are several cases I've seen where one or two small, tiny changes on the page massively reduce the engineering cost by a factor of 10 sometimes. And so it's very important that you and your designers have some kind of relationship where you go, okay, that looks great. If we drop this one statistic on this page, the whole website gets 10 times faster, and then most designers are like, that's fine. Because most designers have an ideal, and they're willing to compromise a little bit. Or a good designer will in fact go, okay, and take that new into account and design around it. Like, their job is not to work in a vacuum. Their job is to work with you and the team to come up with the best end product. And if that means it being faster is a very important part of user experience. So that kind of all plays in the same play. Null forms are great. Don't use defaults, please. Defaults are terrible. If you add a default to a column, when you add it, the database must write the default into every single row it has stored. It has to open every single row on the disk. If you have 1 million rows, it takes a very long time, even on Postgres. Add event rights, adding a column on, we have MySQL, can take us over a day. Because we have so many columns, there's so many rows and so many events and so many tickets. At the moment, adding a column to our schema makes the ops team go, oh no. At Lanyard, we were much smaller, but even then we had a table where adding a column took 15 minutes per column. It had 7 million rows at least. We moved to Postgres, it took less than a millisecond to add that column. But the key thing here is null columns. You need to design your schema so that you expect null as the sort of the empty, the default value. A lot of people go, well, I add a new column, and for everybody existing with this, when actually you can make a small code change and go, well, if none, then assume this, and then save all this time and this stuff. And if you want, you can add it as null, and then slowly populate the default. You can add it as null and say, okay, now update 100 rows, add default, wait, update 100 more, wait, and sort of generally slowly push it in the background. And then when it's finished, do that one adding of the digits, just say, okay, they're all filled, remove the null constraint. The database will scan and go, is anything null? Do a much quicker table scan and go, okay, nothing's null, and then apply the constraint. And that's a much better way of doing it so that things don't go down in production. You will need more than one database. It's very, very tempting to try and avoid this, but if you try and avoid this, you will end up in a horrible, horrible place. As much as I love Postgres, it's not great at some things. I generally would go for things like Redis and Postgres together. The two of them are very good at different things. But there's other combinations too. If you use too many, however, you will be swamped. There's a massive engineering load, there's a massive maintenance load, your ops people will hate you. If you end up with, let's say you have Redis, and Cassandra, and MySQL, and Postgres, and Mongo, and Couch, and React, and something else. Like, suddenly you've got all these redundant databases, and all this stuff, and different driver code, and different querying code, and it's not worth it. So take some time, choose a couple of them, but choose them wisely. Don't spend too much time adding them, and don't be taken away by fancy. A lot of people go, oh, database, shiny, and then go and add a new one to the system. And it's great at one particular thing, but it's really bad at other ones. And so take time, be considered, make a good choice there. Don't just go towards the nearest thing that looks really good and claims to have the performance metrics. In particular, don't trust benchmarks. Benchmarks lie. And in fact, benchmarks are not your website. Most benchmarks are run in isolation for a very calculation-heavy load or a very layout-heavy load. Your website, in contrast, is a very mixed load. It has some I/O, does some waiting around, does some queries, does some other stuff. And so what a benchmark shows may be entirely invalid in your case. And so don't just blindly trust performance characteristics. Go try it out and see, well, something close to what we're doing, or like we hacked around and tried to add it in, and it's running X% faster, X% slower, and so on. Indexes are not free. People think they are. They are very expensive. In particular, adding an index to a table that already is there takes a long time. And even then, like that's an obvious slowdown. You create an index, and it goes down. But even then, you're paying the price every time you write. Indexes are really good. You should have them for things you need them for. But if you change your queries, or you have an index you no longer need, drop it. You'll save disk space, you'll save write time, everything will be happier. And the query plan will be happier too, because it has less things to look at. Relational databases are flexible. It's very, very useful. And kind of the final point here is that a lot of people sort of go, well, I have this really good schema, I need to put stuff into the relational database. That's not true. You can put stuff in there that's schemaless, like I showed you the JSON one earlier. And you can put stuff in there that is, things like comma-separated fields. They're a massive hack, but I'd much rather you had a comma-separated field than you've got a whole other database just to store that one field. Like, because they need to join like Redis to Mongo or Redis to Postgres, and suddenly the whole world of hurt. Like, have you tried joining cross databases? It's not pretty. It's really horrible. Like, you have to sit there in Python going, load all these rows, max them all across, or you do one query per row. It just doesn't end up well. So consider that you can do a lot more than just joining normalized tables. You can denormalize, which is a very good first step. You can have these columns full of rich data as well. And you can do other tricks. Things like Postgres array fields are very good for things like tagging. And so you can do all sorts of tricks like that, and just consider that stuff. Don't be too fixed in your worldview. Thank you very much.
We have time for 5 questions, so please 5 minutes of questions.
So the minute question is perfect.
Yeah, but if I use Mongo, that just solves everything. So it's back to the rows, and the rows fantastic. There's a lot of woo, particularly in the sort of new distributed databases.
Yes.
How do you separate the woo to actually identify what your white patterns are and identify if Mongo may actually solve the problem legitimately, and it's not just a bunch of very over-enthusiastic
So, much like you done last slide yesterday, I'm sorry, but there's no easy solution. The problem is that, as I said before, the way database works is very dependent on your load and your style of the website, and you can't be assured that it's true. On the other hand, there is other stories. Look at other companies, see their sort of use cases, see their stories. Like, for example, I know a lot of companies moving away from Mongo, very few moving to it these days. Like, that may just be a sign of overreaching, that may be a sign of something else. But just sort of, and again, like things like Cassandra versus React, they're very similar, they have different kinds of styles and stuff. And also, at some point, different implementation costs. Like, one may match your coding style better than another one, and that's worth it. Like, at some point, if you're a startup, you're optimizing time to launch rather than actual cost. And so you need to balance time to launch versus actual cost versus maintainability. And even that balance itself depends on your company, how old you are, like how much cash flow you've got, and that kind of stuff. It really depends.
Thank you for the talk. You made a lot of reference, but basically your talk was directed towards people who are building a single site and can choose everything they work with.
Yes.
Some of us are doing either pluggable apps or even just products that are installed by many clients on databases of the client.
Yes.
Do you have any advice for those?
So there is a sort of common denominator issue. So in particular, some of the points I raised are generalized. Things like indexes work very similarly with databases. Things like column types are they're comparable. SQL is an old standard, so things like, especially Oracle, MySQL, and Postgres, they have some common ancestry, and you can rely on some of that stuff. But at the same time, for example, denormalization works great in every framework. Like denormalization, it's the actual performance gain varies from one to the other, but generally, if you have that kind of load shape, that will gain you a lot of time and reads. lose some rights. But yeah, it is a much harder problem. Like Django, in many ways, is held back somewhat by its multiple database stuff. Like, it's really useful and it's a fantastic thing for us, but it means we can't optimize to one specific backend because we have to work with the general case, and the general case includes SQLite, includes MySQL, includes Postgres, includes Oracle, includes Embiez SQL Server, includes Firebird, includes all of this stuff. And like, SQLite is a single disk locked in every access file store. Whereas like some of these, like Oracle Crack is a massively distributed database that can support multiple data sets. And so these tools at scale like very little to share, so it's hard to generalize that stuff.
Thank you very much. That was a great talk. I'm totally stealing that triangle diagram. That was very
it's very scientific.
There's one special, I guess it's, I don't know if I'd call it a special case, very common, which is data warehouse situation,
yes.
Which is a very high volume, very large, high read situation.
Yeah.
That I would not super encourage the denormalization because databases have a lot of DNA for data warehousing situations,
yes.
which use highly normalized star schemas and things like that to keep the size of the database under control.
Yeah.
But otherwise, I think it's great. Thank you.
Yeah, thank you. Yeah, I mean, on that point, data warehousing is it kind of fits here-ish in the diagram. Like data warehousing, for those that don't know, is you have a very large amount of data, and it's intermittently stored in access, but there's still quite frequent reads and writes. Often like things like financial databases, that and stuff. And that kind of sits somewhere on this other triangle, but it kind of doesn't match very well. But as Christoph says, it is a sort of slightly odd way of doing a load that we have to sort of optimize for that stuff. In particular, you don't like denormalization that would blow up the size, and increasing the size would slow. Like, the bigger you go, the slower it gets. Like your disk can only seek so fast. You can only read so much bytes through your CPU's pipeline. So bear in mind that everything makes something bigger. Like making a row longer makes everything slower. Like you have network between you and your networks. Like if I have a row that's 1 kilobyte, that transmits 10 times faster than a 10 kilobyte row. So consider that stuff.
Thank you very much.
Thank you very much.